Well, thank you so much for inviting me here to give a talk, and I say here in quotes, to give a talk to the Girls Inc. And I'm very pleased to be here and talk to you all. I'm going to talk about a mission that we just wrapped up at Southwest Research, and now it's in the hands of NASA. But I'm going to talk a little bit about that and some of what I've done for that mission. So the mission is called Lucy. And one of the fun things about working in the lab is you get to wear these lovely white suits. They're called bunny suits. So we have to have a very clean environment when we want to send things into space. And so that's a picture of me in one of these clean rooms. Um, so Lucy is named after the iconic skeleton that was discovered in Africa, and it's meant to be our origin story. So the Lucy the skeleton is our kind of ancestral evolutionary ancestor, where Lucy the spacecraft is going to several asteroids to look for our chemical origins, to find out how did the planets form, how did Earth form, and when could life have first started arising on Earth. So Lucy is the spacecraft. The instrument I'm going to talk about is called Ralph, or LRALPH, L for Lucy. And Ralph has a camera on it that I worked on called MVIC, and it is a visible and IR camera, and it will take very high resolution images of the surface of the asteroids that it's flying to. Now, these asteroids are in a very special place. They're not in the main belt. You may have heard the main belt. It's between Mars and Jupiter. But these are called Trojan asteroids, and they sit to either side of Jupiter. And they go in lockstep with Jupiter in orbit around the sun. You see that in the little animation here. There's large clouds of asteroids out by Jupiter. So Lucy is going to fly by several of these, and the launch will be in late October of 2021. We are going to fly by a main belt asteroid in 2025, and then fly by 5 of the Trojans. One of these is actually a binary system, which is going to be exciting to explore evolutionary properties. And just recently, one was discovered to have a moon. So asteroids can have moons as well. They're quite tiny. The asteroids themselves are quite tiny, and then the moons are even smaller. But they can have their moons. So that's going to be an exciting thing to fly by. Now, these asteroids sit there because they're what's called a Lagrange point. And it's a gravitationally stable region in orbit around the sun. So every sun-planet system has these Lagrange points. Earth has them. And since they are a gravitationally stable area, we park a lot of satellites out there. L1 is between Earth and the sun, and it's where the SOHO satellite is, and that's observing the sun to give us any warning if there's large solar flares coming towards us. And then we've parked several other satellites out at L2, so that's on the opposite side of the Earth from the sun, very far past the moon. And we have a lot of infrared instruments out there, including the James Webb Space Telescope, whenever it may launch, hopefully soon. And we can have our own little Trojan asteroids. Turns out Earth currently has a pet. It's sitting out at L4, I believe. And it's very tiny. It's right in the little circle. Yeah, very tiny. But Earth is not very massive. So these asteroids come into the Lagrange points, but they're not stable, and then they go flying out eventually. And we'll have new ones in the future, and we've had other ones in the past. We'll lose this one eventually. But Jupiter is much more massive, so it can hang on to its asteroids far better than we can. So why do we want to study these? Well, these are essentially chemical time capsules from the formation of the solar system. These were formed right along with the planets. They got stuck out by Jupiter, and they haven't changed much in the last 4 billion years. So they really are a time capsule to what happened right when all the planets, including the Earth, were forming. We think they have a lot of ice. We think they have a lot of carbons, maybe some amino acids, which would be the precursors to DNA. So they're not a homogeneous population. They're all very different. It's not like we go visit one asteroid and then that explains all of the asteroids. they're actually all very, very different, and each one gives us a different clue as to how the planets form. And we've never gone to visit these. This is a different population altogether, not only from each other, but from the main belt asteroids as well. So all of the missions that you may have heard of that have traveled to other asteroids and even taken samples from those asteroids are all main belt asteroids. We've never had a mission go out to the Trojan asteroids before. So this is going to be a very exciting mission when it happens. So here's the mission. It has a quite, it's a long mission, and it has quite an amazing trajectory. So it launches sometime in late October 2021. The launch window actually opens October 16th and is open for 2 weeks. So we'll hope for good weather when that happens. It will launch out of Florida. And when it launches, it will go around the sun once, and it will fly back by the Earth and get a gravitational assist. So it steals a little bit of energy from the Earth, which gives it a boost in its orbit to give it a much longer trajectory. It saves fuel that way in trying to get all the way out to Jupiter. It flies by the Earth again, and then passes by this asteroid called Donald Johanson. Donald Johanson is actually the person that discovered the Lucy skeleton. So this asteroid was named after him in his honor for that discovery. And so this will be our test. You can see the timeline at the bottom. So we launched October 2021. We are now in April of 2025. So it's going to take that long to get out to the first asteroid in the main belt. And this is our dress rehearsal. This is when we'll turn on all the instruments, turn on the cameras, make sure everything is working properly. Lucy then continues on all the way out to Jupiter's orbit and flies by these first asteroids that are out at its L4 Lagrange point. So there's a whole series of them that will fly by very quickly in 2028. This is going to be the bulk of the asteroids in terms of numbers that Lucy will fly by. Then Lucy will come back and swing back around the sun, come back by Earth, see Jupiter passing by, and then it will get out to L5, where this binary system is. These are very large asteroids in a binary system and are going to be very interesting for our evolutionary understanding of the solar system. We see asteroid and moon systems, but we don't see a lot of asteroids that are almost the same mass in orbit with each other. So that's an interesting evolutionary history for that asteroid pair. And look at the date. We're all the way to 2033. Yes, this is going to be a very long mission, but we're going to learn so much by visiting all of these asteroids. And it takes a long time to get out there. Space is big. So this is an artist's conception. These are somewhat to scale. Now, if we learned anything from flybys of missions to asteroids to planets, they're not going to look like this when we finally fly by them. This is based on the observations we have from Hubble, from ground, from other telescopes. And so this is an artist's conception of based on those images, but in reality, they're probably not going to look like this, but they're kind of close to scale. You can see the binary system at the bottom and all of these different types. The C type has crystals in it, so that was formed in a collision. So that's a very large asteroid that formed in a very disruptive collision. The D types are very similar to Mars's own moons. So that will give us some insight into that system as well. And then the P types are very high and in carbon and are going to be very interesting chemically. We think they're really untouched since no collisions, just been sitting out there by their lonesome for the entire history of the solar system. So, as I mentioned, the asteroids are not going to look like this, which is why do we need close encounters? So this is kind of the quiz as to what is this? This is an image from Earth of a solar system object. And I'll give you a hint that it was made famous by the New Horizons spacecraft that flew by in 2015. And it is, of course, Pluto. That is the discovery image of Pluto from 1930. That's what Pluto looked like when we discovered it. Now, Hubble, our biggest telescope we have in space right now, uh, could see Pluto. We could see features of on Pluto, different colors, different aspects of it. But even with Hubble, that was as good as it got. It was still very blurry. We couldn't see distinct mountain ranges. We couldn't see valleys. We couldn't see any detail at all. So it wasn't until New Horizons flew by that now we can see all of this amazing detail. And this is the same aspect. So you can see the famous heart from the New Horizons flyby, but you can still see the heart in the Hubble image. So it's the same aspect, it's the same side of Pluto in both images. And you can just see the detail quality that we get from these flybys. So we're going to see the detail. So this is another image of the surface of Pluto. Now the camera I worked on, the Ralph MVic, had a version of that on the New Horizons spacecraft. So this is MVic 2.0 that I've been working on. And it's going to be even better. It has even higher resolution. So we're going to even see more detail with asteroids than we could ever see with Pluto. And the detail we saw with Pluto was amazing. So this is going to be really exciting to see what the surface of these asteroids look like. So here's me in my lab. There's the MVic camera. It doesn't look like much. This is sitting, the camera itself is right in there. So that little stripe, you can see multiple colors, hopefully, of that stripe. What is behind that stripe is what's called a CCD, or a charged coupled device. And it's a detector, and that is the exact same technology that is in your smartphone. So every time you take a picture with your phone, you're using a CCD to take that picture. So a CCD essentially is a light bucket. It's just holding there and light falls in, and it registers how much light fell in, and then the software reconstructs that into an image. So it's the exact same technology that's in your phone, a little more less noisy, a little more sophisticated, a lot more expensive, but it's the same technology. And then we put these stripes in front, these different colored stripes are these different filter bands. And so each filter is sensitive to a particular wavelength, and those are tuned to particular chemicals. Each chemical, each molecule is sensitive in particular wavelengths of light. And so in order to see that chemistry that we're interested in, we have these different filter band passes that will be sensitive to the molecules in that chemistry, in that chemical process. So they're long and narrow. So this is very long. There's actually 6 of them there. There's 6 color bands. So there's 6 CCDs. And they're long and narrow because the spacecraft is flying over the asteroid. So just like if you were taking a panoramic picture with your phone and scanning across to take that big image, the spacecraft is doing the same thing. So we don't need a square CCD, but we want a long one to get a very large ground track, but it can be narrow because we're taking a panoramic image. And so my job in all of this, along with my team, was to test, is the camera working the way it should? Does it blur the image? Is it sensitive in those wave bands? Is the filter clear? Are there spots on the filter? It's a glass window, so they can get dirty, and we're trying to, that's why you have to be in the bunny suit and stay as clean as possible. Are there any pixels not working? If you've ever had your camera phone go bad, and suddenly there's a spot in your image, or maybe a dark region or a bright region, those are individual pixels in your PCD going bad. So we have to check all of that to make sure that it's working properly before we deliver it to NASA. And I can happily say that everything worked great. We delivered to NASA in February, and it's been installed onto the spacecraft, into the camera, and everything is working great. So I'm very optimistic that we're going to launch on time. So just in summary, this is going to be the first flyby of the Trojan Asteroids, which is a very different population than we've looked at before. So Lucy, in combination with all of these other spacecraft, are really kind of one more piece of the puzzle to filling in our solar system history. How did the Earth form? How did we get here? All of that is tied up in the chemistry that is locked into these space rocks. So that's why we need to go visit them. And we can't get that information by just looking at them from Hubble or looking at them from the ground. We actually need to go visit them to get that high resolution information. So this is going to be an exciting mission. So stay tuned for October 2021. And thank you all for your attention. So now I would like to welcome Abigail to ask questions submitted by her fellow STEM ambassadors in Girls Inc. Eureka Cohort 4.
Hi.
Hello.
So my first question is, during your research on the explosive death of massive stars, what will be your main goal to accomplish and how long will it take?
Oh, well, so research is always ongoing. So what I didn't talk about is I do study supernova explosions. So very large stars dying explosively and very catastrophically. There is a mission that is going online. It's a ground-based telescope. It's actually located in Chile. It's called the Legacy Survey for Space and Time, or LSST. And it's going to discover several hundred new supernova every night. Right now, we find maybe one or two. So this is orders of magnitude more than we've ever encountered before, and trying to figure out how to do follow-up observations. How are we going to observe these? Which ones do we observe? Because we can't observe all of them, is a big problem. It's a big data type of problem. So I'm working on some code with my team. I have a couple of students that are working on this, and we're trying to decide all of the observations that LSST makes, which one of these are interesting and that we should go look at. So we're trying to get that working before LSST goes online in 2022, I hope, or 2023.
Next question. What were some things that drew you into this career and wanting to study more about it?
Well, I always loved science. I've been interested in science since I was very young in elementary school. And the stars just always fascinated me. There was just so many things to see in the sky. And I was taken out to the middle of nowhere when I was a kid in Maine. We went on vacation out to Maine and the Acadia National Park. And there was a star party there. And I saw, it was so dark, I saw more stars than I'd ever seen in my life. And I thought I was really good at pointing out constellations at that point, and I couldn't even identify any. There were so many stars. We saw satellites, shooting stars. I saw the northern lights. And that really solidified my desire to go into astronomy and see all of that. It really resonated with me.
In the moments where you faced discrimination in your field for being a woman, how did you hold your ground or your composure?
Yeah. So unfortunately, it still exists. I will say happily things are getting better. And certainly in astronomy, things are getting much better. My graduating class, even as an undergrad in astronomy, was 50% women. So we were 50-50. And that's still largely true in astronomy for students. It's not always true at the faculty level, but getting better. So there have been challenges. Engineering is still a challenge, but also getting better. I think one way we get around that and get better is to have more women in the room. And that actually sets to equalize everything. So having more women and more women of color and persons of color in general in the room, I think is how we move forward from all of this. So it's been difficult at times, but fortunately the field has grown. All STEM fields have grown since I was in school many years ago. So you just have to deal with it. And when you deal with it, and sometimes you have to report it and sometimes you can't. But hopefully when all of you have gone on to your careers, this will be a thing of the past and you won't have to worry about it.
Along with that, were there any obstacles that made you rethink your career, and how does it feel knowing that there is a lack of representation in this field?
So, as I said, it's getting better. So, of course, there have always been times when I thought, what am I doing? But um, it helps to know that other people feel that way too. It's called Imposter Syndrome, and you think, there's no way I'm good enough to do this. I can't do this. Why was I chosen for this? Um, and it it's hard, and we all face it. And I think that that's helpful to know that I still face it. I still think, well, I can't do this. What am I doing this for? This is not going to work. Um, but everybody faces that. So I think knowing that you're not alone in thinking that, and surrounding yourself with people, friends, family that have confidence in you and can tell you, yes, you can do this. Yes, you are as good as you think you are, or you're as good as we think you are. Um, uh, it helps a lot. And I said, never, uh, what good mirror is, if you told this to your best friend, what would they say to you? And then you should say that to yourself. Um, and that helps a lot.
Can you share more details on the work and findings with your work on detector subsystems for Scorpio and Lucy?
Sure. So I didn't talk about Scorpio. So Lucy was what I just talked about in the talk. Scorpio, the detector for Scorpio was actually what I was holding in that first image where I'm in the bunny suit. Um, so that's a ground-based instrument that is also going into Chile. Um, the Scorpio is an acronym. I'm not going to repeat it off the top of my head. But that is going onto a telescope in Gemini South. There is a Gemini North. There's two of them. Go fig, same Gemini. And its main purpose is actually to follow up some of these discoveries that the LSST is finding. So I'm very interested in that and using that. So I'm both a scientist by training, formal training and education, but an engineer in practice as well. And that happens quite a bit, especially when you're at a research institution like I am. You may have formal training in something, but then you have to go learn and figure out something else. So we've done a lot of that where hopefully we'll be able to test Scorpio soon. We were on the brink of testing that. We got Lucy out the door, and then we were revamping the lab to do the Scorpio testing when everything locked down. So hopefully we will be testing that soon. But I'm on a wait and see too for that mission.
What propelled these comets out to their present orbit so far from the sun?
Well, so the asteroids are around. So comets and asteroids are a little bit different. Asteroids are mostly rock, where comets, you may have, hopefully you've seen Neowise, that's up in the sky right now, is mostly ice. So it's a different composition. These asteroids actually just formed out there. So most of these asteroids probably originated either near Jupiter or near where the main belt asteroids all formed. So it's just the leftover debris that didn't make its way into a planet. And they're where they are now because of Jupiter's gravitational pull. So it's sitting in those gravitational wells that are stable, and so they eventually migrated there, and could stay there for billions of years just because it's a stable orbit to be in. Anything that's not in a stable orbit either gets kicked out of the solar system or migrates into something that is a stable orbit. So after billions of years, you just have stable orbits left. So that's where it's at.
Final question. You've built your career on your love of science and math. Given that you formed your career with the love for the stars, what would you hope to see for the future of astronomy and girls in the field?
Well, it's definitely a growing field. There's a lot to be done. James Webb Space Telescope is going to be pretty revolutionary in terms of what it can see. And we're discovering all sorts of new things with gravitational waves and merging black holes and all new exoplanets around weird stars. And what is dark matter? What is dark energy? So there's a lot of questions in astronomy that we still don't know the answer to. And I don't even know if we're going to find the answer to any of these things in my lifetime even. But it will be hopefully in all y'all's lifetime. And there'll be questions for you to answer, for the future of astronomy and future astronomers to answer. And I hope the field keeps growing in diversity as well. And I think it will. I think there is a big push to increase diversity and in both astronomy and in all STEM fields in general. So go forth and do good science.
Those are all the questions that I had.
Great. Well, thank you very much for asking very insightful questions.
No problem. Thank you.